Okay, and I'm going to try to get through these, the last few questions, just in one video. Okay, so assume that f of xy is a real valued function of the variables x and y. If x naught, y naught is a critical value, and we have some knowledge about the Hessian, can we determine whether or not x naught, y naught is a local min, local max, or saddle point? And here, the star entries for this question and the following, the star entries just mean we don't know what they are. Okay, so notice what's going on here. This says that the double x derivative is equal to 1, and the double y derivative is equal to minus 1. So like in the x direction, if x naught, y naught is a critical value, in the x direction, this says we have a local min in the x direction. Because the second derivative is positive. So if we hold y constant, it's like we get a local min. Okay, on the other hand, this is negative. So it's like saying we have a local max in the y direction. Okay, so we have a local min in one direction and a local max in another direction. And so this tells us that it has to be a saddle point because, again, we have a local min in one direction, a local max in the other direction, and we're at a critical point. Okay, another way to think about this, if the function satisfies Clairaut's theorem, which it doesn't necessarily satisfy Clairaut's theorem, but if it does satisfy Clairaut's theorem, then you know that these two star entries are equal to each other. And so the determinant is going to be minus 1 minus a positive number because the stars are equal. So when you take their product, it's going to be positive. So overall, the determinant is negative, which means you have a saddle point. Okay, now this is a similar problem. Assume that f of xy is a real valued function of the variables x and y. If you have a critical point, and this is the Hessian of f, can you determine whether or not x naught, y naught is a local min, local max, or saddle point? Now, in general, the answer here should be no, because we need to really have more information about the stars. But if f satisfies Clairaut's theorem, so let's just think about it this way. If f satisfies Clairaut's theorem, then we can write this. The Hessian is going to be 1. We'll say fxy, fxy, 2, and the determinant of this is equal to 2 minus fxy squared. And we have no idea whether this is positive or negative. So even if f satisfies Clairaut's theorem, we don't know whether or not this is positive or negative, which means we cannot determine whether it's a local min, a local max, or a saddle point. But if it was, anyways, again, that's even if we know f satisfies Clairaut's theorem, we can't do this. And if we don't know f satisfies Clairaut's theorem, then we really can't do it because we have no information about the starred entries. Okay, so now let's look at part 6. Okay, so similar to the last one, if we don't know that f satisfies Clairaut's theorem, then basically we can't do anything because we don't know anything about the determinant of this Hessian. But if f satisfies Clairaut's theorem, in other words, if xy of x naught, y naught is equal to fyx of x naught, y naught, then we know that the Hessian evaluated at x naught, y naught is equal to 1, 1, 1, 2, and the determinant of the Hessian evaluated at x naught, y naught is equal to 1 times 2 minus 1. So this is 1, which is greater than 0. So we know we either have a local min or a local max, and notice that since fxx is greater than 0, this means it is a local min. Again, this is just like the second derivative test from Calc 1. If the second derivative is greater than 0, we know we have a local min. And notice also that fyy is greater than 0. Okay, so this one is a little bit different. So we know we have a local min. We know x naught, y naught is a critical value. What can we say about the start entry? Well, it's a local min. So local min means that fxx and fyy are greater than 0. Okay, so we know right away that the start entry has to be greater than 0. But let's look at something else. Let's compute the determinant. Let's see if we can get even more information. The determinant of 1, 2, 2, and I'm just going to call this fyy since that's what it is. Notice that this is fyy minus 4. Okay, and observe also that since we know it's a local min, we know that this is greater than 0. So what this tells us is that fyy has to be greater than 4. Okay, so that's the more information that we can determine. Notice also, I could have changed this question a little bit, and I could have added less information here. So if x naught, y naught is a critical value, and furthermore, you know that it is a local min or local max, okay, and this is the hash, and then what can we say about the star? Well, since the xx derivative is positive, that would tell us that it's a local min. So if we have a matrix like this, and this is the Hessian, and we know that it's either going to be, we know that x naught, y naught is either a local min or a local max, and we know that the double x derivative is positive, we know it's a local min. Okay, so fxx, this means the second derivative in the direction of 1, 0. And so this isn't, might not necessarily be very common notation, but I think it's expressive. So let's say fuu means the second derivative of f in the direction of u. And similarly for other vectors. So if x naught, y naught is a critical point, and fuu is 16, and fvv is minus 2, then can we determine whether or not x naught, y naught is a local min, local max, or saddle point? Well, the idea here is that in the u direction, the point x naught, y naught is a local min. Why is it a local min? Well, the second u derivative is greater than 0. And in the v direction, x naught, y naught is a local max. Why? Well, the second v derivative, in other words, the second derivative in the direction of v is negative. Okay, so again, this is just from Calc 1. If the second derivative is positive at a critical point, it's a local min. If the second derivative is negative at a local point, at a critical point, it's a local max. So in some directions, x naught, y naught is a local min, and in some direction, x naught, y naught is a local max. So this is exactly what it means to be a saddle point. So x naught, y naught is a saddle point. Okay, and so this is similar. So similar to the above, if the second u derivative is 16 and the second v derivative is 2, then can we determine whether it's a local min, local max, or saddle point? Well, we know that x naught, y naught is a local min in the u and v directions. But we do not know if it's a local min in any other direction. but we don't know about any other direction. So the answer to this question is we can't determine it, because in some directions we know we have a local min, but we don't know about any other directions. So it's inconclusive. The information we have is not enough to conclude. And that is the end of this practice test.